The following work is based on our snake robot Cobra. Cobra consists of 11 joints alternating between pitching and yawing and 12 links. The head module consists of an Intel RealSense D435i stereo camera and IMU for sensing, and an NVIDIA Jetson or an NX as the primary processor. The rest of the body modules are identical, each carrying a battery for power and a servo motor for a single degree of actuation. This work targets autonomous navigation for Cobra in an unstructured environment with space constraints. We assume accurate mapping, localization, and planning using the onboard sensors, and focus on a framework for motion modeling and closed-loop path tracking given a predetermined path. The video on the left shows Cobra moving with a nominal sidewinding gait. The key challenges to address with such a movement are: there is no stable base for a reference frame that can be used for tracking, the shape and footprint of the robot varies continuously during the gait, and the large number of discrete contacts make contact force determination challenging for any sort of dynamic modeling. We address the first two challenges by simplifying the system into a variable size bounding box with its center coinciding with the center of mass of the robot. As the robot executes sinusoidal gaits, the bounding box remains relatively stable, providing a reference frame for a tracking controller. To achieve this, we simplify the robot geometry into a series of point masses located at the start and end of each link. The center of mass of the robot is calculated by taking the average position of each link of the robot weighted by the mass of the link. The orientation of the center of mass is calculated through a singular value decomposition of the matrix formed by stacking vectors from the center of mass to each link. This yields the principal axis of inertia of the robot, which also remains relatively stable through the oscillatory gait. The bounding box is then formed by taking the limits of the link positions in the center of mass frame. To address the last challenge, we use a kinematic motion model that assumes links in contact with the ground do not slip, which is a valid assumption for quasi-static movements. We identify links in contact with the ground by assuming flat ground and assigning a contact signal of 1 for the links within some small threshold epsilon of the base of the bounding box. We represent the kinematic model by stacking zero velocity and acceleration constraints for each link that is in contact with the ground. This results in a system of equations where the only unknown is the acceleration of the base frame, solved for using a least squares approach. We then numerically integrate the base frame acceleration to predict the motion of the robot. Using this motion model, we can now formulate a gait generation framework. We abstract away low-level joint trajectories with a central pattern generator and solve for CPG parameters of amplitude, frequency, and phase using a nonlinear model predictive approach. In each iteration, we minimize the path tracking error subject to constraints of the motion model and, crucially, the size of the bounding box based on the available space. If required, we can add additional constraints here for task-specific objectives such as stable camera trajectories or sensor coverage during motion. We validate the model by executing a simple sidewinding gait in a high-fidelity SimScape simulation shown in the video on the right. Below shows the estimated contact signal plot against the actual contact signal reported by the simulator. Next, we use this to predict the center of mass movement for a 1-second horizon at various points in the trajectory. The result shows agreement in the direction of movement, though there is a large drift in the distance traveled in each horizon. We then test the model on a scenario where the robot employs gait switching to navigate through a narrow passageway. This shows the high-fidelity SimScape simulation of the setup. We also demonstrate execution on the hardware platform. The resulting visualization shows the kinematics of the robot, the estimated center of mass position and orientation, and bounding box throughout the trajectory. This is based only on proprioceptive joint data and pose estimate of the head module using the stereo camera and IMU, calculated using the reduced order model presented in this work. We also use the simulation to study contact forces and contact patterns, which are challenging to observe on the hardware platform. In summary, in this work, we have developed a reduced order model for a path tracking controller for a snake robot, developed an NMPC framework for gait generation, and demonstrated stable bounding box estimation in real time on simulation and hardware. For next steps, we plan to improve contact modeling for reducing drift in the motion prediction, close the loop with sensing and optimization for generating gaits in unknown environments, and implement a bounding box based path planning framework that helps us navigate constrained spaces.